distracted. And if you have any questions or observations in the course of this lecture series, kindly drop them in the chat box and they will be attended to. Again, welcome, and I'm certain that we will have a fantastic learning session with Dr. Obi. So here's the agenda, so you see how everything will go. Do we have Mr. Stephen Obo on the call?
Yes, I'm here. Good morning, everybody.
Good morning, sir. Good morning. Lovely to have you this morning. So, sir, kindly take the welcome address.
All right, thank you. Again, good morning, everybody. My name is Stephen. I'm the student chapter liaison chairperson for Lagos section, and we're happy to be introducing us to this petroleum engineering lecture series, where we'll talk through from how oil and gas is found, how it is being explored. We'll also go to how the drilling phase looks like, drilling and completions. We'd also talk about how production engineering looks like in terms of the various separation and bringing the oil to the tank, trying to separate the oil, gas, and water. And finally, we'd also talk about some economics on what is the best opportunity for us to actually invest in. It's going to be a 4 weeks program, but for today, we have the opportunity to have a great personality of Dr. Ifeanyi Obi to come share with us the geoscience aspect of petroleum engineering as a field, and we believe is going to do great justice because I know him very well. So just one thing I want to charge us all is to be keep an open mind, take notes. And one other thing we're trying to achieve with this is for universities that do not take petroleum engineering, but really want to understand what is going on in this oil and gas industry, this SP they belong to. This is an opportunity for them to actually educate, to be educated on the concept of oil and gas. Again, finally, to also mention that this program is brought to us in courtesy of the Society of Petroleum Engineers, the Lagos section, and also bring it further down to the student affairs team. But I must also say a big thank you to VA, who also was part of organizing this, and also thanks Ms. Joy for coordinating this today. Thank you very much. I look forward to learning a lot as well for myself. Thank you.
Thank you, Mr. Stephen, for the welcome address. Okay, now to welcome our speaker, or to introduce our speaker. Dr. Ifeanyi Obi is a seasoned geophysicist with an MSc in petroleum geology and PhD in applied geophysics from the University of Nigeria, Nsukka. With over a decade of industry experience, he has worked at Shell Nigeria Exploration, ExxonMobil, and currently Seplat Energy. He is the founder of GeoCamp Institute, an online platform for geoscience learning. Dr. Obi also serves as the SEG representative for Sub-Saharan Africa, a member of the SEG Global Council, and students coordinator for AAPG Africa region. Additionally, he is the University Assistant Chairperson for NAPE. Through research, mentorship, and leadership, Dr. Ifeanyi Obi remains dedicated to advancing geoscience education and industry innovation. So if your hands are not too busy, let's put our hands together in the chat box as we welcome our speaker for today, Dr. Ifeanyi Obi. Dr. Ifeanyi, can you share your screen, please?
Thank you very much. Good morning, everyone. Can you hear me? Just to reconfirm again.
Yes, sir. I can hear you.
Okay. I'm trying to share my screen, and it is coming up. Let me know when you see it. Yeah, is anything showing yet?
A minute. I think it's still loading, so you have to give it a minute.
Okay. All right. So while it's coming up, thanks for the warm introduction. Sometimes it's kind of bizarre sometimes to hear people talk about you and you're like, okay, is that me? Is that someone else? But yes, so this is me. Thanks for the very warm introduction. I understand this is a gathering of petroleum engineers mostly, from the invitation. So my hope is that at the end of the day, this will be something that we'll all learn, and we'll pick out at least one thing. The idea is to pick up one thing from the class, not necessarily everything, and let's see how much we can, get better in our knowledge of the petroleum industry and with respect to exploration. And what is petroleum, first of all? How do we find it? Where does it occur? And what else about it that we need to know? Okay, so let me know. I think the screen is slowing down here, but I'm not sure why. Let's see, give me one more minute. Is it showing at all, or it's still coming up?
Oh no, it's showing now. We can see it clearly.
Okay, better. All right. So again, I'm going to apologize profusely. This is it was quite of a short notice for me, and I don't have a pack, prepared for today. Before now, so I had to do a lot of grab things from everywhere, including a few pictures that I have. The idea is to just stimulate a discussion on what is this petroleum, what about its generation, how does it get to where we find it in the subsurface, and then ending where we are. So that's what I try to summarize in this picture for now. Hold on, give me a second. Let me try and do something on the setting. See if it's gonna help. Enable share sound. And then let me hide float screen. Okay. So give me a second. Okay. Trying to hide something on my side. Okay, good. All right, so this is it. We're going to talk about petroleum. What's the key? What do we need to know about each generation? How it migrates to its place of residence, which is a trap, and then accumulation. And then we're going to look at maybe a couple of surface occurrences, videos of where some evidence of hydrocarbon in form of gas or oil on the surface. And then we'll see how much we can talk before we close. Okay. So let's quickly jump into generation. How does this happen? What is the origin of petroleum? Okay. So now there are two key schools of thoughts regarding the generation of petroleum. I'm going to dwell heavily on the biogenic theory, but there is a lot of early comment about the biogenic theory, which kind of suggests that the hydrocarbon we see today are from non-living sources, abiotic sources or abiotic sources.
Doctor,
yes.
Your voice is cracking, sir. Sorry to interrupt. Your voice is cracking.
Okay, so it must be a network issue then. Did it even improve by any chance?
Is it possible
No.
to put off your video, if it could help?
Okay, I think I even tried to do that. I thought I did that already. All right, give me a second. Let me. Okay, video is off already. Can you see a video?
So we can see your screen, but the issue is your voice is cracking. So
No,
Okay, you
it's
know what?
network.
yeah.
Yeah, let me take off the headset and just use my regular voice.
Okay. Thank you.
Hello.
Yes, we can hear you, sir.
Okay. Okay. Um, is this being recorded?
Yes, the meeting is being recorded.
Recorded. Okay. Let me know if it is any poorer or better. Let me know if I need to switch my internet provider, because that might be the issue here.
So we would appreciate if you could switch the internet because there's no improvement.
Okay. Let me see.
Okay.
All right.
Thank you so much. Just confirm.
No, it's fine. Let me just try something else.
Kindly stay on the call as Dr. Ifeanyi will be with us shortly. We apologize for this slight inconvenience, but he'll be with us shortly.
Okay. I try to change. Just let me know if there's any improvement on the network.
Yes, it's perfect. You can hear you very perfectly, sir. Thank you so much.
You have to have like 2 or 3 different sources to survive.
Thank you so much, sir.
Okay, let me try and share my screen again. Okay. Let me know when it comes up.
All right, it's currently loading. Yes, now we can see your screen.
Okay, so it's up okay now, right?
Yes, sound is perfect and we can see your screen very well. Thank you.
Thank you. So I was saying that just quickly regarding the generation, there are two schools of thought. So what I'm going to try to do is to avoid talking about what, because I know we have mostly students in here and young professionals, trying to avoid saying or repeating things that I know are typically taught in schools. So I'm going to try to just cut down on those as much as possible. So key thing is there are two schools of thoughts. One school of thought is petroleum is of abiogenic origin. In other words, it has come from non-living sources, right? And then there's another school of thought that says it is from living things, and there's a bunch of reasons for that. Some signatures we see in petroleum, we also see it in living things in terms of the chemical content, and a lot of other content reasons for that. So that's just one thing to keep in mind as an engineer. There are two schools of thought, but dominantly what most of the petroleum industry of today is going by is we really characterize petroleum as being of biogenic origin. In other words, living things, they are buried and they are converted in absence to a form that generates what we call kerosene, and eventually that changes at higher temperatures and pressure with further changes to petroleum. So that's kind of the simplistic way to put it. Okay, there's something we call petroleum systems. Petroleum system, we're talking about two key things. 4 items which we call elements of petroleum. We have what we call the source rock. Source rocks are generally rocks that are rich. They have a tendency to be able to produce hydrocarbon or petroleum. So they are so rich in or the content that produces hydrocarbon that we call them source rock. We have carrier beds, which could also be, sometimes part of a source rock or what we call reservoir rock. But the key thing is that they are typically migration pathways, helping to go from the source to the reservoir. We also have a reservoir rock. Reservoir rock is like a storage tank. Any rock that has the capacity to keep petroleum or hydrocarbon is called a reservoir rock. It could be what we call siliciclastics, it could be carbonates. But in this part of the world, in Nigeria, in most part of Nigeria Delta, we have dominantly what we call plastic rocks. And then we have another element called trap and seal. Trap is basically any configuration that can keep hydrocarbon in place, right? Arrangement of rocks that can keep hydrocarbon in place. While a seal is a rock that can prevent hydrocarbon from escaping further to the surface. I will show you a few examples of where hydrocarbon has escaped to the surface. And then there are other components there that we consider: maturation, migration, and timing. And these are all elements that, right, we consider in this system. So processes are very important that we talk about. So the figure to your right is just showing generation, migration, accumulation, and then you have some schematics showing how works. Okay. So I've talked about source rock, any rock that is capable of generating and expelling hydrocarbons to form commercial oil and gas pools. And one thing that they're very known for is fine-grained rocks. I mean, when you say fine-grained, it means if you look at the rocks, they look very smooth, and it's a characteristic that they're known for. And another thing that they're known for is the total organic content of these rocks are very high. In other words, they are rich in materials. In other words, remains of dead in organisms, plants, or animals. The hydrocarbon ratio, of course, is also very high. And typically, these rocks are deposited in the absence of oxygen in the environment. So they're buried rapidly in the absence of oxygen, which is what makes it easy for them to get converted to a form where those contents, the organic content of the rock, converted to what we call kerosene and then eventually petroleum. This is just a picture of some examples of what will pass as source rock. The one to your top left is taken from somewhere in Enugu State. These are what we call shales, dark gray or black shales, and they have a bunch of work that have been done in these areas to properly understand these rocks. They're on the surface. Interestingly, today they're on the surface because of what we call tectonics. They are now exposed in the surface. But one thing you will notice is that it's dark in color, and most rocks, especially shales. And then when they are carbonates, they may not be dark in color. If you look at the bottom figure, you will see shale limestone at the bottom. It's limestone with some shale components. And then the one in the middle is nodular limestone. Limestone will be great source rocks because it's a combination of, it's a rock that has a mixture of, remains of dead organisms that make up a particular kind of limestone, especially the ones that are rich potential source rock material. So this is just showing an example of what source look like on the surface. And then these are other pictures. And by the way, these pictures are pictures that I also have taken, the ones I just showed you. And then this other one also are also pictures. So what you will notice is that they are generally dark in color. Sometimes for the ones that are shale, fine grain or fine or fissile, what we call fissile shale. They are rich in organic content. They are usually dark. They buried rapidly in the absence of oxygen, which is why they are able to actually get converted to a form where it's able to give.
Sorry to interrupt again, Dr. Obi. So in the chat box, people are complaining that your voice is breaking and they can hardly hear you. So if you could please make your voice a little louder so people can hear you, sir.
Yeah, so it must be the network though.
Yes, I was going to say that it could be their network as well, because
it could also be on the other side too. Yeah? But if one person here can hear me clearly, that means it is on the other side. But if everybody can hear me clearly, then I'll know that it is mine.
So we can hear you very well, Doc.
Okay, great.
Yeah,
so,
it's just the notification of people coming in and coming out of the meeting.
Okay, maybe that might be also bad.
Yeah.
Okay.
Yes, it's bringing this.
Yeah.
So we'll turn off the notification sound. Just give us a minute to get that done. But you can continue,
okay.
sir.
Okay, all right. So for those who are geologists, I know you might find this a little more fun. With the pictures in Bida Basin in Lokoja, Kogi State. The one to your right is from that one is in Ogun State. These are pictures that I have in my archives, and the one on the bottom. So but the one on the bottom left, what we go to the left is from the US. That's not my picture. That is borrowed from the internet. But these are just examples of source rocks, how they look. Okay. And if you progress to the next slide, let me just move to the next slide. So what we have there. Now, these rock rocks are folks we call geochemists. We have geophysicists, geochemists, but this guy primarily is to do some kind of analysis and kind of find a way to characterize the source rocks. How good is the source rock? And they have a bunch of parameters that they use, and which is what we have here. Total organic carbon content, the hydrogen carbon ratio, the quantity and quality, and there are other data, the Tmax, the hydrogen index, the oxygen index, and a bunch of this. So at the end of it, they use all these parameters to determine what is the quality of this rock as a source of petroleum. Okay? And that's really primarily their duty. And the good thing is in Niger Delta, we have world-class source rocks. They are what we call, there's a formation we call the Agbada Formation. It's rich. And then we also have other source rocks that are from other related area. But the good thing is in this part of the world, we have source rocks. Just give me a second. Let me attend to someone who is trying to do a presentation. Give me a second. Okay, sorry everyone, I'm back. So the geochemists, this is their job, and then they go ahead to give us a picture of the sequence of what happens. I told you the source rock is a bunch of living organisms, plants and animals dead that have been buried together with what we call sediments, and as the depth of burial progresses, as it gets buried deeper, one on top of the other, it gets converted in the absence of oxygen to what we call kerogen, which is more like an intermediate item. And then with further burial, increase in temperature, increase in pressure, conversion of that organic matter content of the rock to a different form, oil is generated. And then if that continues, it gets to another phase, gas. So you get oil first and then followed by gas, because each of these have certain range of pressures and temperature that they are very stable. Gas is where things have gone beyond normal. That's where you find gas. And this is the same principle that we use in exploration. We expect to find oil in a certain range of, conditions. And then as you go much deeper, where things are more intense, you'll find less of oil and more of gas. Okay, so that's one thing to keep in mind. And thanks to all the geochemists and all the subsurface folks, this is what we know today. Now, a little bit about kerogen. I think I'm going to read. I'm not going to read this. What I will say is that kerogen is the intermediate member between the organic matter that was buried, and then the oil and gas that we have. It's largely an intermediate product that is very complex, very complex. A lot of work has been done on the content of kerogen. It's very complex. But the key thing is that the trajectory of the conversion of kerogen determines what you get. What ratio of oil and gas do you get? What kind of oil? Is it heavy oil? Is it light oil? Is it more oil than gas? So that is all a function of the content of the kerogen. Is it dominantly plant source? Is it alga or other source? And then what is the condition? How did it progress in terms of burial? That determines whether you're getting one type or the other. So now we have what we call different types of kerogen. So type 1 kerogen, this is the property. They are largely formed from proteins and lipids. Of course, proteins and lipids are things that we're probably familiar with. Okay, so they readily produce liquid hydrocarbons. That's one thing with type 1 kerogen. Most people in the oil and gas are happy with this because we like oil, right? Of course, we like gas too a lot, but dominantly people like oil because, again, type 1 kerogen, this is the property and this is where it comes from, and this is what is the precursor for that. The hydrogen to carbon ratio is there, oxygen to carbon ratio is there, but largely these are largely of bacterial, freshwater algae, and some plant content. Type 2, similar, but I think the key difference here is that type 2 kerogen ends up giving us a mixture of oil and gas. That's the key thing I need you to take away. Type 2 kerogen, mixture of oil and gas. And then we have other types of kerogen, type 3, which has its hydrogen to carbon ratio and all of that. But the material is mostly gas, what it produces. And that is largely because the content of type 3 kerogen, the precursor or the parent, is mostly of plant matter. What that means is that what was buried in the absence of oxygen, if it is where it is dominantly plant content, you'll be getting type 3 kerogen. And what that will give you in the long term or as a product will be mostly gas. And then we also have other types. The one that has, that one that is type 2, oil and gas, but rich in sulfur, that is called type 2S kerogen. And then type 4, which is another form that is mostly a bunch of aromatic hydrocarbons. So this is a kind of a complex diagram showing how, beginning from the living organisms, which is either plants or animals, they're broken into lipids, protein, and all of that. And eventually, as things get buried, as this deposit gets buried, it gets converted from kerogen to bitumen, and then it gives you petroleum. And then if you go to your left, you're getting light oil and gas, and then eventually gas. If the precursor is largely protohydrocarbons. And then if the precursor is largely lipids, proteins, and carbohydrates, to give you more of, heavy oil and pyrobitumen all the way to your right. And then you see the temperatures where these changes occur. And then if you notice, you also notice what we call diagenesis, katagenesis, and metagenesis. These are just terminologies, big words that define ranges of conditions where rocks are converted from one form to the other. So there's something we call hydrocarbon generation window. Okay, so keeping it short, oil window and gas windows. That's the two different windows. And these are basically ranges of temperature and in some cases depth where you find dominantly oil or dominantly gas. So what we do as subsurface scientists will be to understand what we call the barrier history of sediments. Of course, we already know the content of the sediment. Is it shale? Is it sand? Is it rich in organic matter? And then we do some kind of, create some kind of a forward model to say, okay, what happened to this through time? And then figure out whether at a certain depth, will this rock at this depth, will it be within the oil window, given the temperature gradient, given the burial rate, given the content of the rock itself and everything. And with that knowledge, we're able to figure out that between the depth of 5,000, for example, to 8,000 is the oil window in this area, and deeper than that is a gas window, meaning you'll be seeing more of gas. So there are a special group of people who do all of those work, basin analysts, geochemists, they do all of those work to figure out, okay, what is the depth range where you see dominantly oil or where you see dominantly gas? And they use a lot of, inputs from knowing the rock type, the temperature, the geothermal gradients of that area, the pressure, a lot of all this information to create a model that tells you what that depth range and temperature ranges are. Okay. And this is also what generates what we call this plot you're seeing here, oil window. So everything above the oil window, in quotes, will be classified as immature. In other words, if I drill a well into a field between a certain surface, let's say between the surface and a certain depth that I think is immature, I will not see oil and gas that are, that is worth my while. But if I go deeper, I will see oil accumulations. If I go much deeper, I will see more of gas. And at a point, I may not be seeing even much, maybe mostly rocks that have turned to charcoal also because of the depth that they have been buried. So this is all taken into consideration in deciding whether a field or whether an asset or whether a basin, is prolific or not. This is where it all starts. I don't know, I'm going to go to migration, but I don't know if there are questions now, or I don't know how you want me to take it. Take the questions later or just keep driving on. Let me know.
So we would have all the questions collated at the end of your presentation, sir.
Okay.
Or at the end of your lecture.
And I apologize. I know I'm also racing a little bit because I know it's a kind of a huge pack, and I want to go. Okay, so now having spoken about the origin generation, of course, whatever is generated has to move to somewhere where we want it to be, right? So that brings us to the top concept of migration. So migration really is every process that involves the movement of what was formed as oil or gas from one location, which is called the source, to another location, which we call the reservoir. So from source to reservoir, whatever happens moving through from one to the other is called migration. There are different understanding in terms of the types. Primary migration is primarily within from the source rock through the process of diffusion or pressure, mostly around the source where it came from. And then secondary migration will be every process that helps the oil or the gas or the hydrocarbon to move from that source through what we call pore spaces, as well as buoyancy effect to a final location, which is the reservoir. So that's secondary migration. And then if you look to your left, you see what we also have highlighted here. Primary migration mechanism. If you see what it is, it's largely within the source and across. But secondary migration is, in this case, you see that it's within what we call the reservoir, which is where the oil, which is the host, the home for the hydrocarbon, okay, within those pores. And there are other schools of thought that there might be tertiary, but this is primarily the two main types of migration. So this sketch, this sketch you're seeing is also to further demonstrate how they are expelled from the source rock, which is usually deeper than the reservoir rock. Reservoir is usually above sometimes, most times. So because of pressure, the hydrocarbon is squeezed out from the source. It finds its way through the reservoir, and it keeps moving up until something keeps it from getting to the surface. Okay, and this is an example. These are actually live cores, and these are pictures that I also have in my archives. This is just highlighting cores, but filled with hydrocarbon fields. There's something we call fractures or faults, micro faults. So these lines here are like, micro faults or breaks, or cracks, you may call it, in the subsurface that the hydrocarbon has found as pathways in moving. Incidentally, this is within the reservoir, so they're just here. Okay, so in exploring for this, we also look out for oil shows and things like this in subsurface photos and cores. This is this is a sketch. I think I have a video on this also. I think I'm going to show it also. A surface occurrence of hydrocarbon. There's something we call oil seeps, where oil in the subsurface goes from the source to the reservoir. It keeps moving up until it gets to a point where it is supposed to be trapped, but for some reason you have fractures or cracks, and then the oil finds its way through those cracks, just like we saw in the previous slide, and it gets all the way to the surface. And then we see those surface occurrences in the form of oil seeps or oil pools. Okay. Hopefully, I'm going to be able to show a video or a small 1 or 2 or 3 clips that I have for this. So this is all speaking about migration. Again, this is another picture I also I have, hopefully, to also show to show you a lot about migration. So this is showing what we call oil, heavy oil actually coming out through a certain layer of rock. This is taken from Okitipupa. And these are real. You go in there, you touch this, it is oil oozing out of the rock on the surface. And that is because the oil in the subsurface has found its way through some cracks and it's made its way to the surface, and we're seeing it out there. I think I'm going to also show a video of where you have bitumen coming up to the surface from leakages like this. Okay, so now I haven't spoken about migration. Let's talk about storage. If you think storage, there is one word that comes to mind: tank, reservoir, space. What is it that can keep it? What is that storage? What is that storage mechanism? And that's the reservoir. Okay, so reservoir, of course, I'm sure we're pretty familiar with what it is. For those of you who are familiar with this word, almost everybody, I think, any place where something valuable is kept is called a reservoir. But for us subsurface engineers and scientists, it's a 3-dimensional body of rock where hydrocarbon are located. It could be sand, it could be carbonates. In some cases, you also find it in fractured basement rock, surprisingly. But yes, those are unconventional reservoirs. But dominantly, when I say reservoirs, I'm speaking to clastics, which means sand in this case, dominantly sand, because that's what we are more familiar with in this part of the world. So they begin their journey from a parent rock. These reservoirs, in terms of formation, they start from somewhere, and through time, they get, transformed to a form where they are finally deposited, and then oil can find its way and get stored in them. And I'm going to show you, I was going to say that for this talk, we're talking more on plastics, which is our focus of this for this presentation. So these are surface occurrences of reservoirs. So you go on, what we do as geoscientists, we go out there to study rocks. A bunch of people look at us as bushmen or people that are probably a little crazy, just standing around looking at rocks. But that's the beauty of it. We need to understand what we see on the surface to give us a better picture. Yes, thanks, Shay, for that. So we need to understand what we see on the surface or at the surface to better understand what is buried thousands of feet below. Okay, so we see it here, we draw a model, and then it gives us a better picture of how to relate to the ones that we don't see, that we only see when we drill well. Okay, so this is a surface example, beautiful pictures in my archives. This is taken from Salt Lake. And then this is also another example from my archives, taken from here in our own Anambra Basin in Southeast. So these are classic examples. Sandy, oil will find this place a very fun place to be because it's got the pore spaces. It can keep oil and gas. And then this is another example. This is, again, a picture I borrowed. It's not mine. But these are just showing core photos, just like the previous one I showed before. Sometimes the reservoirs can get really what we call indurated, and they are not so, in terms of pore spaces, you don't see a lot of it. Sometimes they are fractured, like you're seeing on the one on the left. And these are all different things we do to characterize the subsurface. We go from the surface, we look at the cause, and we try to integrate what we will learn to better understand the subsurface. And that helps us in our estimating how much of oil or gas we have in whatever subsurface accumulation that there is. Okay. So these are also other elements that I just thought to put this together. So as subsurface scientists and engineers, what we also do is we don't only think of the rock in terms of, okay, this is a fun thing to look at as rock. No, we think in terms of depths. At what depth is this reservoir in question? What is the pressure? What is the temperature? How does that affect the oil and gas accumulation at that depth? I talked about oil window. How does it affect it? How can I recover the oil in that reservoir? And then the geoscientists will talk more about the lithology or rock type. What's the porosity? What's the permeability? What is the strength of the rock? Will it fracture at certain conditions? And then some other fun fellows called engineers, of course, also petrophysicists will now start talking about wettability. They are trying to understand how will the rock relate to fluid. Okay, they talk about wettability, effective permeability, relative permeability, and capillary pressure. These are all important for us to better understand this storage container called reservoir, and for us to better characterize whatever you have stored in the reservoir rock as hydrocarbon. Now let's talk about traps. Yeah, I'm showing you a fun picture of a trap in literal sense. So what we do in the subsurface as scientists and engineers will be to, find out what are the arrangement, what configuration can keep oil in place. Okay, and then we also ask the question of how and when did this happen, because it's important to keep in mind timing. At what time did oil, the hydrocarbon, migrate into this reservoir? As at that time, was the reservoir in a shape, did it have some kind of configuration that would prevent the oil from escaping? Does it have a seal around it? Does it have a geometry or the shape of like an anticline or a dome? Can it keep hydrocarbon? So these are the questions that are typically asked. And that's what this other figure will also help us understand. How do we find oil and gas? What we do beyond understanding the geochemical basis, the rocks, source rocks, are they mature? We ask ourselves, is there a reservoir? We've looked at that, okay? And the answer to that is yes. The next question will now be, okay, are the reservoirs sufficiently, are they sufficient enough in terms of their capability, porosity, permeability, and all of those? And the answer is yes. The other question we'll now ask is, okay, when did the oil move from the source rock to that reservoir? As at that time, did we have a seal rock or a trapping configuration to prevent the oil from going all the way further to the surface? Because nothing stops the oil from getting to the surface, right? So we find a way to better understand, okay, what oil move into it? Did we have faults that will allow the oil to escape to the surface, and all of those? Okay, so this is just that example. And then this other one shows, again, a typical trap configuration. You see where the oil rigs are placed? They are placed on the top of the anticline, what we call an anticline, or what some people might call a dome. But what you see to your right is that everything potentially works, right? The oil is trapped. If you look at the figure, the oil is trapped. But you know that gas has a higher capillary entry pressure. In other words, gas can still force its way through and get to the surface, even when the oil is trapped. So gas can be leaking gradually while oil is still in place, because gas has a lot more energy to pierce through the rock cracks. And then to your left, you also see that this configuration is not to your left. You see that the trap is not properly formed. Okay, the reservoir rock here, which is this white patch with the orange dots, gets all the way to the surface. So whatever oil that's making its way from the source rock gets here to the first reservoir, is trapped. When it gets to the second reservoir, it goes through these faults and migrates, and it finds its way all the way to the surface. And that is just how what we saw at Okitipupa, the bituminous deposits there, and what we also saw at in some parts of the east in Enugu, oil seep. I'll show you the video. This is how it happens. The oil found its way through some crack or force and gets all the way to the surface because the trap failed. But in some other scenario, what it tells you is that if the trap failed in one location, nearby, you might have a place where the trap is successful, just like you're seeing to your right, where the oil is in place. Okay, and this is showing just an example of a subsurface representation. This is seismic data. This is the data I worked on, and I think it's been published in 2018, a paper published in 2018. But the idea here is to show you how even the subsurface can be very complex. So I'm showing you two things here. The seismic is the subsurface, right? This is in Niger Delta. While to your bottom left, this is on the surface. This is somewhere in Ireland. These are just showing you examples of how the surface occurrences can help us better understand the subsurface. You will see this analog we see on the surface here, right? This is what it looks like when we do a sketch of it. And this is how we go from the surface to the subsurface, because at the end of the day, it's the same signature, right? The seismic data you see here is subsurface data. But again, you and I are not there. We're only looking at images and trying to make sense of it. And sometimes the quality of your image may not be very instructive. So you find a way to use analogs or other offset data to better understand what the trapping configuration is. So these are some other fun surface examples. These are not from the internet. These are pictures that I also have taken. Very fun representation of traps. This is a case where the rock has been squeezed. Look at this nice anticline. This is another what we call chevron fold. The rocks have been squeezed and deformed significantly. Here, these rocks have been squeezed and stretched, and here they've been stretched. So these are all things that might lead to creation of a trap one way or the other, but these are all structural traps. And then in looking at this generally, we try to, again, I'm thinking subsurface here, both engineers and geoscientists. We look at everything, okay? The faults, the internal features, the external features, what's the volume, what are the boundaries, what are the aquifer limits? My friend here, Stephen, of course, they know a lot about aquifers and all of that. And then the permeability, waterability, those are things that are all considered in characterizing a trap, okay? And that helps us understand what we expect to find. You see here, we have reservoir here, we have non-reservoir, that's like a seal rock, and then we have another reservoir that has gas up here, oil down here, and water. Again, this is just a representation. This is a surface picture. I just tried to do a cartoon on it. But what you see is this is how we do the characterization of the subsurface, right? Using an example like this to better understand what we have down there. And then in search for hydrocarbon, we take seismic data, what we call seismic data. So generally, seismic data is just like taking a picture of the subsurface, okay? You send some vibration and it releases some waves. You record how long it takes for the wave to, the signals to reverberate to the surface. And then you convert that duration into a picture, right? In milliseconds, and that's what we have. Different rocks will give you different reflection time. And at the end of the day, what we as subsurface scientists do will be to interpret these different colors and figure out which of them is a reservoir that has oil in it, okay? And then in some cases, we're lucky, we drill a well, like you see channel A and channel B, and we're lucky we find what we expect. And then we progress to create a 3D map like this. In this case, all these reds here are the oil and gas column. And then at the end of the day, we progress to give you some kind of estimate of how much it is, keeping in mind parameters like what we call the formation volume factor, the gas expansion factor, and conversion factor. A bunch of all of those. We're working with engineers. At the end of the day, we're working together to come up with a volume of what we expect in the subsurface. So I'm going to quickly close by showing you some surface occurrences of hydrocarbon. Again, these are pictures that I also have taken. This is a well. To your right is a well where they were literally fetching heavy oil or bitumen from about 12 feet from the surface, from where the guy is standing, 12 feet below. So they dug the well and they were fetching it. And then this is bitumen all the way on the surface, pouring out somewhere in Okitipupa. And then this is a wellhead that was drilled. I heard it's the first well that was drilled by British Petroleum in the past. We were there for some field expedition. I think we've seen this already, surface seep. And then we also have another occurrence of surface hydrocarbon. In this case, it happened in Anambra State, where we have gas flares coming up on the surface. So there were this company, they were drilling for water. And along the line, they started seeing what looked like fumes. You know, they thought it was a broken pipe. And then it turns out it's actually natural gas coming from the subsurface. It's just endless. And then eventually became fire after some time, because the gas, of course, got ignited, became fire, and it was burning for days, weeks before the experts came to put it off. Okay, so this is just showing you that this thing called hydrocarbon is real in the subsurface. It finds its way to the surface through fractures on cracks, and sometimes it tells us whether a certain area could have successful trapping mechanism or not, or hydrocarbon in place. Okay, so I'm going to end with maybe a few videos if you have time. Let me just quickly switch to that.
Dr. Ifeanyi, are you there?
Yeah, I'm here. I'm trying to pull up. I have two videos. Let me, hopefully the first one comes up. I'm trying to put it up.
Okay.
Okay, first one is almost up. Share this screen. And for people who follow me, I have a YouTube channel. Some of these videos are already in the public domain. So yeah. So I'm going to play.
If you can provide your name on YouTube, so you can drop it, or you can type it in the chat box so people can
I'll put
follow
it in the
you.
chat box. Yeah. Okay.
So
this is showing the surface occurrence of hydrocarbon, what we call oil seeps in Ugueme. Hello everyone, this is Ifeanyi Obi. I'm going to do a brief talk on petroleum seeps, also called oil seeps. An oil seep is a location where hydrocarbons in their natural liquid or gaseous forms escape to the Earth's surface normally as low-pressure flows. These fluids find their way to the surface when released through rock fractures or faults, or sometimes due to capillary leaks or mechanical seal failures. I have a few pictures here taken from an oil seep outcrop in Ugueme, southeast Nigeria. Occurrences like this are good surface indicators of a potential hydrocarbon system. If you take a closer look, you might notice oil and gas molecules probably escaping from a subsurface trap and making their way to the surface where it mixes with a pool of water. Some slow-paced circular motion also noticed are probably indicative of entry points where the fluid seep into the pond. Thanks for listening. Until next time, stay well. Okay, that's the first one. Just give me a second. So the second is an interesting one. It's I actually captured the bitumen that got to the surface real time, and that was really something really pleasant to see. So let's see how that happens together. The second is almost there. That's the wellhead we saw earlier on. an abandoned well head. This is the this is 01. Let me forward to contact. So what you will see some bubbles. That's very good. And there's some sound in the background. So that's bubbles. These are gas bubbles coming out. Like that's real. And we got to another point. I was very lucky to have this a rare capture. For some reason, I zoomed in on this bubble and real time. That's it. That's it coming out. That's what the cement to the surface, and then from an opening, then goes all the way and makes it products. So this is our natural resources coming to the surface and just floating away. Yeah. Someone showed this video in a program in a school in Japan. And they were really shocked that we have oil bitumen coming on the surface. And the question was, what are we doing about it? And I'm not going to answer that question for you. Okay? So let me stop here. There's one more video and then the third one is actually a video of the gas flare. I know a lot of you might have seen it, but for those who haven't seen it, this is just to bridge the gap. Yeah, coming soon.
Maybe the rain moved in. Now water from somewhere.
So what you're seeing there is the actual water mixed with fire, and then of course the gas coming from the subsurface, and it was there like this for a long time, at least 3 weeks. It was burning constantly, day and night, And this is an area where there's no pipeline passing underneath, nothing. They were just drilling for water, and this happened. And this is not the only case. There've been a couple of other cases like this, but this is a video I took in 2023 when we went to visit them.
When we came on Monday, it was two.
Vapor like. I don't know because you are continuing.
All right, so I'm going to end it here. Let me just say thank you for having me. I do hope it was worth your while, really, this morning sharing. Thank you very much.
Fantastic session, Dr. Obi. We're so glad that you shared this knowledge with us. Thank you so much. Please give Dr. Obi a round of applause in the chat box. If you learned something, you found the lecture insightful, kindly give Dr. Obi a round of applause in the chat box. Thank you so much, sir, for this lecture. Really insightful, very interesting lecture indeed. Thank you so much, sir. So we have a couple questions. Can you hear me?
Yes, go ahead. I can hear you.
Okay, so we have 2 questions now. I would implore participants to drop more questions. Okay.
Okay.
So heading now to the first question. What did you say, sir?
No, I said I was checking the chat box to see.
Okay. You want to read them yourself?
No, it's fine. Go ahead. You can read. Yeah.
Okay. Well, if you want to, it's fine. Maybe you can. So you can
let
understand.
Me read. Maybe it might be faster that way. Yeah.
Yes.
Okay.
Thank you.
My question goes this way: is the method of drilling? So from Musa, is the method of drilling hydrocarbon same as that of water that we know? Yeah, they're the same principle. You're drilling, you figure out the depth at which where you expect your water table to be. But for oil, it is deeper, and it's a lot more complicated because it could be risky. Gas, of course, can cause fire. Oil itself, they're under pressure, they're deeper. So, but then it's the same method of using, trying to drill and get down. And as you're drilling, you're trying to, case to ensure that the wells, the rocks don't cave into the space. But for oil, it's a lot more complex because you have multiple layers of casings. You will have prepared to know at what depth, what is the pressure. The rig is more expensive. The rig for that, whether land rig or so, it's more expensive. But it's literally the same principle of just digging a hole until you get down to where you think it is, basically. The next question says, what answer the question? No, I didn't get that. Let me quick scrolling down. Yeah, I'm seeing applause. Thank you very much. Thank you.
So before Musa's question, there's one ahead of it. Ike Dinachi asked the question. It says, with the emergence of AI, how could that affect the industry and its career prospects?
Yeah, so AI is AI. AI, remember, is garbage in, garbage out. AI will feed on what you put in it, what you project, what you program. But truth is, it is an evolving discipline, and the industry is also keying into it. To be honest, the industry is keen. In fact, the tool I'm using now, there is a part of it that says AI. Like there's a particular tool that is, and so the companies are intentionally the software vendors are intentionally building in AI components, AI modules into it. So what I normally advise people is do your best to catch up with the trend. Really, the industry will not be left behind. Trust me, because the industry, of course, especially the oil and gas industry, they like to stay ahead and they like to stay in tune with development. So yeah, it's evolving. It is happening. You may have heard of machine learning. A lot of things that you normally predict mechanically in the past. Now, machine learning is one thing that is being used to predict, for example, mapping your horizons and faults. With machine learning, you're able to figure out, without doing a lot of work, what are the regional faults, how complex is this? And then you now, as a human, go in there and select the ones that are different or that are more important. So AI is coming in heavy, coming in hot, and the industry is not lagging. It is now up to us to try and develop ourselves and be ready and be positioned to be relevant as things evolve. And I don't know if there are other questions that I've not seen. I'm trying to scroll.
Yeah, so I'm not seeing other questions yet.
Yeah, I've not seen. I don't know. I mean, that makes me feel like
there's one here.
Okay.
There's one here by Chinedu from Federal University of Technology, Owerri, says, "Sir, the oil traps that you talked about, are they created naturally or man-made traps?"
The traps that I have and I showed are all natural traps. Like none of them is man-made. You can argue that activities of man can cause a tremor, like some kind of local earthquakes, which can create mini fractures, micro fractures, right? You understand what I mean? Like fractures that might lead to oil or hydrocarbon that's under pressure escaping through those fractures. That might be action of men. But largely, a lot of what we have seen are natural. They've just been there, really. And along the line, something happens, a fracture that has been there opens up, and you see the gas or oil on the surface. And then the ones on the subsurface, of course, those ones are all natural. All those pictures you saw, those fancy pictures about those what is it called? The anticline and all of those physical surface pictures, of course, those are natural. And if that was buried in the subsurface, that's exactly what it is. That's how it happens. So it's natural.
All right, sir. So that brings us to the end of our question and answer session. We want to say a big thank you again to Dr. Ifeanyi. Thank you. Oh, one more question dropped. Would you mind if we take that one more question?
Please go ahead. If you leave me, I'll keep going till 2 p.m. But
yes, sir. You are such an amazing, I would say, lecturer. So you're an amazing lecturer. Thank you. Thank you so much. So the question is, which kerosene type is more prone to finding hydrocarbon?
So it depends. Oil is hydrocarbon, gas is hydrocarbon, right? So if you're talking about oil, it's type 1. The one that has more of that has a high hydrogen to carbon ratio, not so high oxygen to carbon ratio, and from algal material. Like meaning the precursors were mostly algal materials, right? Buried in marine conditions and all of those. That's type 1. Type 3, which is more of plant source. So if you go to the swamp, those of you who are probably I'm from Delta, if you're from Bayelsa or Delta, you go to the swamps, all those your swampy areas. Imagine that 20 million years ago or 100 million years ago, that area as it is now got buried. All those plants are buried just the way they are, and are buried rapidly in the absence of oxygen. That thing gets converted to a type of kerosene that is rich in type 3, and that will dominantly give you more of a gas content. Okay, so type 1 is oil, type 2 is oil and gas, and then type 3 is dominantly gas. And they are all hydrocarbon, just to clear the air. Oil and gas are both hydrocarbon.
Apparently, people don't want to stop asking questions. The session was so interesting that they just keep dropping questions, even though we're out of time.
So I can put my email out here. And then,
yes, please. So the people will redirect their questions to you, sir. If you could just drop your email in the chat box so people could send their questions to you.
Yeah, and then I have a YouTube channel where I also have videos. Again, it's for free. So this is not an advertisement. It's for free, basically. Well, for now. So I have a number of yeah, for now. Things can change, right? Please. So
no problem, sir. No problem. Please also put in your YouTube name so we can follow you and we can learn more from you, sir.
Mr. Moderator, you skip my question, please.
Apologies, Sir Lawad. Apologies, sir. Let me see if it's something we can take or if you can just send it directly to his email.
No, we can take it.
Okay, can you retype your question? Because I'm trying to find it and I can't.
Yes, I just want to know more about primary migration theories. Thank you.
Okay.
So primary migration will be from the source, within the source, expelling the oil out of the source rock, but due to pressure, due to some kind of pressure and some buoyancy, but at that level within the source, squeezing the oil out. But secondary will be from the source into the reservoir, and then mostly within the reservoir, within those pore spaces in the reservoir. So those are secondary reservoir. But primary is every process that helps the oil move out, squeeze out the oil from the source rock away from it. That is primary migration. I don't know if that helps.
Lawal, did his response answer your question correctly and perfectly?
Yes, sir.
Are you satisfied? Okay, great. So to the rest whose questions we could not take, we apologize. Please send your questions to his email. It has been provided. Okay, so we're moving on now to the next session, which is the photo session. So please, if you can, show us your faces, your beautiful, your handsome faces, so we can take a picture. I will take a screenshot. Yes, please. So can we have more people showing us their beautiful faces so we can take a screenshot? Wonderful. Let's have more people, please.
Yeah.
Okay. You may want to mute yourself. Show us your face, but we don't want to hear your private conversations. Thank you.
I would really appreciate the organizers of this.
So my
Can you have more people turn on their camera, please? Because just okay. All right. So
Also, please kindly mute yourself. Thank you.
Please, the video is on mute by the host.
oh, okay. Oh, apologies. I will. Let me. What's the name, sir? Please. Sorry.
Lawrence Willie.
Let me see. Apologies. I think. Okay. Okay. You can go ahead, sir. All right. So. All right.
Yeah.
Yeah, Dawn Joy. Dawn, I'm Dawn Joy. So we can.
Fantastic. Thank you so much, Ovie. Please,
Thank you. I'll
can
be
you
logging off
take
now.
the...
Thank you.
Oh, no. Oh, Mr. Okay, that's fine. Ovie, please, can we have you take the closing address?
All right, good evening. Sorry, good afternoon, everyone. Many thanks to Dr. Ifeanyi. It has been a very insightful one. And many thanks to our Student Affairs Chairman, Mr. Stephen Obo. We've had several questions around this topic because we have within us some chapters that have been, that don't have petroleum engineering departments in their, in the school, but because of some sort of interest, and not just the interest, because of the value that SPE brings, which is why we saw it needful to have this program kickstarting our petroleum engineering lecture series. Many thanks to you, Dr. Ifeanyi, because for me, like Engineer Steven said, I picked a lot of learnings from all what you shared, sir. And I want to believe I'm not the only one, because I'm already getting as many testimonies and thank yous from the back end here. And many thanks once again, Dr. Ifeanyi. And this is not the end. This is not the end. We hope to have you again. And yeah, thank you so much. And also, I want to say very big thank you to everyone person who had joined on this call. And like I said, I want to believe that you were able to take as many and load your truck, your truck of knowledge on this topic. And you also want to do some due diligence, make some findings on all of the things Dr. Ifeanyi has shared to broaden your horizon about this topic. And going forward, we want to see everybody win. And I see that SP Lagos section, we are on top of it. And many thanks once again, everyone, and most especially Dr. Ifeanyi. Thank you.
Thank you
All
very much.
right. Thank you so much, Ovie. Thank you so much, everyone. Thank you, Dr. Ifeanyi. Thank you, Engineer Stephen Obo. Thank you so much for joining in. We hope to see you next time. We have come to the end of this wonderful lecture. Thank you. So you can log off now. Thank you. Bye, everyone.